Yeah.
Hello, everyone. Thanks a lot for joining today. We have Steph Foulds from, I don't know if I'm going to pronounce it right, Strathclyde University. It's a pleasure to have you. And we will start with a round of introduction from the audience, as usual. So I'm Lila. I'm a third year PhD student with Alex, working on quantum algorithms for chemistry.
Hi, I'm Alex, a chemist with interest in model algorithms and research within it.
I'm David. I'm the head of quantum chemistry at Continuum, a quantum computing company. I basically coordinate the activities of the research team that deals with algorithms and applications of quantum chemistry and quantum computing.
Hi, I'm Griffith. Did my PhD with Alex a little while ago now, and now I'm a research scientist at Continuum in the Beach Group, looking at various state projects for capturing.
Hello, I'm Tara. I was also a PhD student with Alex, and I'm also a scientist.
Hi, I'm Troy. I'm a third year PhD student in David Joshua's group, and I'm looking into exploring and doing quantum computing.
Hi, I'm Andrea. I'm a junior research fellow in the chemistry department, so looking at quantum computing for quantum chemistry algorithms.
I'm Dylan. I'm a first year PhD with Alex, and I'm doing non-orthogonal configurations.
Hi, I'm Luke. I'm a master's student with Alex, and I'm looking at quantum computing.
Hi, everyone. I'm a quantum algorithm developer at Cambridge Consultants. I'm working right now mostly on quantum error correction and basis estimation.
Do we have anyone online?
People online, would you like to introduce yourselves?
Who knows?
Dylan, I know you're here. No, we can start.
Cool. Hi, everyone. Thank you very much for inviting me. Yeah, I'm Steph. My PI is with Kendon at the University of Strathclyde in the CNQO group, although apparently we're going to be changing our name soon. But basically, the theory of quantum information and quantum computation group at Strathclyde. My background for my PhD was more quantum information-y, to do with quantum entanglement measures. But recently, for my postdoc, I've been doing stuff on quantum walks that I'll tell you about today, specifically with some near-term error modeling. Yeah, and these are my funding bodies. And this is the archive paper. Cool. So, oh, this was working. Never mind.
Oh, maybe you can split.
I just put it in the
Need to what, sir? Thank you. Okay, so I'm going to do a very short intro into near-term quantum algorithms. Some of this stuff I've heard that you're thinking about already, but I'll go through it somewhat quickly. We're often looking for some sort of quantum uniqueness or speed up that utilizes the exponential mapping of resource to space, often uses quantum entanglement or write-only memory, meaning that you have some qubits that are involved in the computation, but you don't read them out at the end, and they're useful because of quantum entanglement. And then also the complex negative state amplitudes that can mean that you have constructive or destructive interference. But my personal bugbear is that often complexity analysis for this kind of thing doesn't take into account the readout problem. So the fact that often we have our exponential state space and we need to read out all of those states, and therefore we need to do many, many repeats of our algorithm in order to get the many, many readouts. Ideally, you would have a single state to read out at the end of your algorithm. That's usually not the case. Hardware constraints. Often quantum algorithms are hardware agnostic. I personally think you should be thinking about which hardware your algorithm is suited to as early as possible, because then you can start to think about that as you develop your algorithm. and end-to-end algorithms. So by this, I mean that your algorithm includes literally everything that you will need to do from start to the end. So state prep, encoding, your actual algorithm, decoding, readout. Often complexity analysis does not include this, and it means that any speed up or advantage that you might get in your algorithm is destroyed by your state prep or readout or whatever. Quantum hardware. I think you'll be familiar with all of this. I'll specifically be talking about neutral atoms, but a lot of what I say about what is specific to neutral atoms is also common to ions. My extra criteria, as well as the well-known criteria, is that the hardware must suit specific algorithms applications. If your hardware can do all of these things, but isn't actually good for any specific applications, then what's the point? And therefore, as I said, I think we should do hardware-informed quantum algorithm design as opposed to developing your algorithms and then at the very end trying to figure out which hardware you should put it on. So, quantum walks. Quantum walks are based on the classical random walk. This is simply if you're doing a random walk on a line, you have your line, you have your walker, which starts at the origin, you have some kind of coin, you flip your coin. If it's heads, you go left, if it's tails, you go right. Very, very simple, but a very powerful method of computation. For quantum walks, it's exactly the same, except that you have a quantum walker and a quantum coin, which means that your coin is in a superposition of heads and tails, and your walker is in a superposition of left and right. What this means is that you get much further spreading with the quantum. So, for example, with the classical, you basically, on average, don't get very far from the origin. You're just oscillating around the origin. But the quantum, because of those interference effects that I told, those constructive interference effects that I told you about last time, you get these big peaks away from the origin. What this translates into is quadratic speed up for search problems and exponential speed up for routes across a network. Again, these are speed ups in principle and not end-to-end speed ups. So you want to make sure that you have a speed up in principle, but then you also want to make sure you have an end-to-end speed up. Quantum walks are also universal in quantum computation, so not necessarily efficiently, but you can do any form of quantum computation with a quantum walk. These are some of the really cool papers in the last couple of decades that talk a lot about continuous quantum walks, discrete quantum walks, the mapping between the two, these quadratic and exponential speed ups, again, in principle. Yeah.
Right.
Yeah.
So I'm not familiar with quite what is up there, but it looks remarkably similar to what you get from the Hamied polynomial that comes in a harmonic oscillator. And is that effectively what that's looking like? Is the square of the Hamied?
So I'm not actually sure, but it is basically just like photonic. So all of these peaks are to do with odds and evens. In a quantum walk, you'll only ever have odds at one step, evens at one step. Does that sound like it's the same?
Well, there's definitely an odd-even parity, and it usually involves a propagation of, I can't remember, a recurrence relation that looks, I think, pretty similar to what's effectively happening here. So,
interesting.
yeah, thank you.
I'll look that up.
I'll try and work out whether it is that.
Okay, and then the other thing that we'll be looking at is neutral atom quantum processes. So the cool thing about neutral atoms, so they're held in optical traps like this. They're all identical by the very nature of them being atoms, which means they're you can get them high quality and they're highly scalable. The other really cool thing is that they're dynamically reconfigurable qubit arrays, which means that mid-circuit, you can pick them up and move them around. As long as you do that slowly enough, that's an errorless movement. And it means that we can get really high connectivity because you don't need to do all those swaps. You can just pick them up and move them. High fidelity 1 and 2 qubit gates. High fidelity for quantum computing. And important for this application specifically, native multi-qubit gates. So far, they've only done 3 qubit gates in the lab, but in theory, you could have your rank of your multi-qubit gate is only limited by your architecture of your array. So at the moment, we've only got 2D arrays, but in the future, we want 3D arrays. And then your multi-qubit gates are only limited by how many atoms you can get in a specific radius. These are some really cool papers that come out recently, basically achieving these capabilities. You can see that a lot of them are super recent. It used to be that neutral atom fidelities weren't as high as all the other hardware. Recently, they are as good as or surpassing other hardware. Okay, so the first motivation for looking at quantum walks is that they're a toy that they map to the lattice Boltzmann method for fluid simulation. Specifically for this project was the toy model for lattice Boltzmann method. So the reason that they map so well is that lattice Boltzmann looks very, very similar to quantum walk. So as I said, you have your coin step, and then you have your movement step. That's very, very similar as a collision step and a transport step. And you can map these exactly onto each other. And in fact, there's a paper that talks about the fact that quantum lattice Boltzmann is a quantum walk, and therefore they map very well. You can also potentially do SPH with quantum walks, but they don't map quite as cleanly. The other thing that motivates the inclusion of lazy quantum walks in this project is that LBM requires a rest state. So that means basically, as well as your velocities going in specific directions, you also have a chance of staying in the same place, a rest state. And that, as we'll see later, maps to having self loops on the graph that your walker is walking on. Yes. The other motivation, and probably the more relevant motivation, is as an algorithmic benchmark. So some really interesting work has come out of, so specifically for this paper, out of our group, to do with benchmarking neutral atom processes. So this paper here finds the quantum volume for a 9-qubit neutral atom quantum processor, and it's the same as superconducting. It also finds that in the case of Grover's algorithm, having native CCZ gates is better than only having native CZ gates. So instead of decomposing all of your 3-qubit gates down into 2-qubit gates, you instead use the native 3-qubit gate, and it has a higher fidelity, or at least in the case has a higher algorithm fidelity for the Grover's algorithm. Also, another cool benchmarking paper that came out was looking at nearest neighbor versus all-to-all connectivity. So specifically, again, looking at the ability to pick up atoms and put them where you like mid-circuit. Again, finds that you have higher algorithmic fidelity when you have this all-to-all connectivity. And then the other thing that comes together to motivate this work is that we have very accurate, effective matrices for CZ, CCZ, and C3Z gates with a neutral atom computer with current technologies. These are near to optimal. They could be improved by, for example, 3D geometries, but they give us a good idea about what our control gates actually look like on near-term neutral atom computers. So because quantum walks specifically, and encoded quantum walks, which we'll be looking at, that look like this because they include many multi-qubit gates with their rank scaling as the size of the graph. I'll go into this in a bit more detail later. It means that quantum walks is benchmark and encompass effective or native multi-qubit gate fidelity, qubit connectivity, and then all the normal things like qubit coherence, span, etc. Span meaning state preparation and measurement. So very quickly, so we all know what we're talking about. Our quantum states look like this. Complex and negative amplitudes, which contribute to our constructive interference. The gates that we'll be using, X gates, rotation around Y, controlled X gates, controlled Z gates, which look specifically like this. Sometimes it's 1, 1, 1, -1 instead of this. But just a convention, but this is the specific native gate for neutral atoms. Looks like this. And then also CKX and CKZ gates, which just mean that we increase the number of controls on our Z. So if you're not familiar, control X is just if your control qubit is in 1, then your target qubit gets the X operation applied to it, etc. And then these CKX and CKZ gates just have a greater number of control qubits. And they all have to be in 1 in order for the operation to be done on the target qubit. So we're specifically looking at encoded quantum walks, which means that we're not doing a physical quantum walk. We're not having our atoms physically move like the walker does. Instead, the only the amplitudes in move around the walk. So for example, if you have a 4-node graph that's encoded in 2 position qubits, like this. And then we have 1 coin qubit, which is just your heads or tails, whether you're going clockwise, anti-clockwise. And then again, we have lazy quantum walks, which just means that the graph that we're working on has self-loops. So like this. This means that we need to increase the dimensionality of our coin. We could, of course, do this by having a 3-dimensional coin or a qubit, but because we're doing near-term neutral atom modeling, we instead use 2 qubit coins, 1 for the normal clockwise, anti-clockwise, and 1 for rest or step. So again, our gate circuit looks like this. This is specifically for the 1 qubit coin quantum walk, so the standard quantum walk. First, we flip our coin. We specifically, for this simulation, we have a 50% chance of going clockwise, 50% chance of going anti-clockwise. In a real application, we would tune this in some way, but we really only care about our shift operator, so we've just made this super simple. In real applications, this could, for example, be controlled on our position or something like that. We have our n position qubits that encode our 2 to the n nodes in our graph. And then we have the increment, which is the part of the shift operator that goes clockwise. And it requires multi-qubit gates, effective multi-qubit gates of n plus 1, of rank n plus 1, and then rank n minus 1, all the way around down to 2 qubit gates. And then you just do an x to flip them all. Obviously, these 2 x's would cancel out, but it was just easier to represent it like this. And then you do the decrement, which is anti-clockwise, exactly the same, except that you put an x gate in front of each of them in order to do the decrement. And then you repeat that as many times as for as many steps as you want your walker to do. So this is for 1 step. And then at the end, you measure your position qubits. The lazy or the 2 qubit coin quantum walk looks very, very similar, except that we add our extra qubit and then we control everything on that qubit. Okay, so gate decomposition. Our model includes native 4-qubit, 3-qubit, 2-qubit, and 1-qubit gates, but our circuits require higher rank qubit gates. Therefore, we're going to have to decompose. These are the numbers of what that looks like. Yeah, and also it requires ancilla, so our qubit count will go up slightly. Yeah, look at the paper to see all of the decomposed circuits. Okay, so we're going to be modeling using our neutral atom quantum processor, specifically an array of cesium atoms in a triangular or rectangular array. So I should change that. We have our two hyperfine states, 0 and 1, that make up our computational base states. And then we also have our super highly excited Rydberg state that is only an intermediary state. It's not part of our computational basis. Rydberg states experience dipole-induced pairwise interaction, which is how our control gates work, that I'll mention in a minute. Specifically within the blockade distance, so for example, these 3 atoms here, and we construct our array such that every 3 atoms, or in the case of a rectangular array, every 4 atoms are within the blockade distance. And key thing is that within this blockade distance, you can only have one Rydberg excitation. If you try and excite so there's coupling between one state and the Rydberg state specifically. If you try to excite from 1 to the Rydberg state for an atom that already has a neighbor in the Rydberg state, it will detune and it will fall back down to the 1 state. So,
Sorry, could you repeat that?
So,
Try and excite.
if you try and excite, so if you have, so for example here, if you have here, if you already have one atom in the Rydberg state, and then you have another atom next to it within the Rydberg blockade, and you try to excite it to the Rydberg state is detuned, so it's slightly off energy-wise, and so it won't manage to get there, and it will just fall back down into the 1 state.
So that's an energy thing. That means it doesn't.
It's an energy.
Yeah, okay.
Because when you pulse it up here, you pulse it up to this energy level, but there's nothing to catch it.
You had some E states looking around in your.
So that's just an intermediary state. That's just the way in which it's a 2-photon excitation. You just have to go via this E state. It makes it
But that doesn't stop the
more errorless.
blockading.
No, there's no. It's not part of the Rydberg blockade. It's just how we get to the Rydberg state. So we use this Rydberg blockade to do our multi control gates or our single control gates. The process is that you pulse from the 1 to the Rydberg state in 1 atom. You pulse from 1 to the Rydberg state and then back down again for the second atom, and then back down again for the first atom. And basically it means that because of the Rydberg blockade, it means that you enact a control Z or multi-control Z gate. However, this obviously isn't done perfectly. We have gate errors from spontaneous decay, so decaying when we don't want it to, and a finite blockade radius. That just goes in the error model. And we model these imperfect operations with effective matrices. Is that the next slide? Yes. So specifically in our model, we model them with these CPTN, so completely positive trace non-increasing maps. which basically just means that they're physical. I usually just call them effective matrices because it's easier to say. And they look like this. They were derived by Dirac in our group in this very cool paper. And I've shown CZ and CCZ for you here, mostly so that you can see that their amplitudes and phases are in terms of how many atoms are pulsed up into the Rydberg state, because that's where the error comes from, largely. Yeah, and then C3Z follows a very similar pattern, but it's too long, so I haven't put it up here. Therefore, we get fidelities, where fidelity is specifically defined with this, of 99.81 for our 2-qubit gate, 99.54 for our 3-qubit gate, and 98.5 for our 4-qubit gate. We assume that our single qubit gates can be done with perfect fidelity, which means that when we transform our CKZ gates into CKX gates, they have equivalent fidelities because you only need single qubit gates in order to map those two to each other. So aside from our gate errors, we also have spam and passive noise. Passive noise meaning when a qubit's waiting to be acted on, its state will decay slightly. Yes.
So the effective matrices up there, they only account for simultaneous decay.
So I believe they also account for finite Rydberg radius,
Okay.
but
So those fidelities, they are kind of governed by physics, like it's not a technological issue at this point. Is that right?
it's both.
Ah.
So these are what we can currently do in the lab / near term, but this is the ideal of what we can currently do in the lab.
Oh.
So these will improve with better technologies, but only slightly. The things that will improve these fidelities are things like 3D arrays, better laser power, but probably only slightly. It's a bit difficult to predict.
Yeah,
but
because the spontaneous decay is only going to have some
Mhm.
Yeah.
Okay. 2 species arrays, which they're developing at the moment, will also slightly increase the fidelities.
Okay.
But I think all of this is slightly.
These effective matrices, they're measured, or could they be calculated?
So they're calculated. These are
Okay,
calculated.
right, okay, calculated. So,
It's purely physics.
yeah,
Purely
purely
physics.
physics based. And we know enough about the states and the interactions that these are accurate to at least that presume. Does that make sense?
Yes.
Yeah.
So if you look in the paper, I also say the best that we've achieved in the lab, and they're slightly less than this. So again, this is like ideal of what we can achieve in the lab right now. But so it's still got things like the current laser power that we have in the lab and stuff like that as part of the model, but you're never able to get exactly your ideal in the lab just because of yeah. Exactly.
And you require a temperature of
So I think these are actually 0 Kelvin,
0 Kelvin.
but they usually do a couple of Kelvin in the lab. So again, that will slightly change the fidelities. So the actual results of the simulation. So basically, I have a code that puts in the realistic modeling for gates, spam, weighting error, and then I do it for several different sizes of quantum warps. So what we have here is we're specifically using the native gate set with So I've ignored the single qubits with CZ and CCZ. So far we aren't using the 4-qubit gate. This is therefore nearer term. So for example, the lab in America could be doing this right now, but the lab in Strathclyde couldn't be doing this yet because they only have 2-qubit gates. So, and these are the fidelities again. So what we have here on the x-axis is the number of steps that we run the simulation for. It's not each step of the walk, it's we ran the quantum walk for that number of steps and then did a readout. On the y-axis, we have the Helena fidelity, final state fidelity after the walk, where 1 means that we got exactly what we wanted to get, and 0.5 means that our state is orthogonal to the state that we wanted it to get, and then 0 is opposite of what we wanted to get. 0.5 is terrible. In the x's, we have the results from the IBM quantum computer. So this isn't exactly a faithful comparison because these are real results and these are simulated results, but it gives you sort of an idea. And also they didn't do lazy on IBM. They only did the standard quantum walk. So we have in pink, we have on a 4-node ring, in blue on an 8-node ring, and in yellow on a 16-node ring. And then we have standard, lazy, standard, lazy, standard, lazy. What we find, first of all, is that they're grouped together in terms of the number of qubits they require / the size of the maximum effective gate rank that they needed. So that's why a lazy quantum walk on a 4-node ring and a standard quantum walk on an 8-node ring have very similar fidelity results. It's because the biggest source of error are those multi-qubit gates and are the readout. So you will find that the ones with a higher qubit count, higher position qubit count, will have a slightly lower fidelity, and that will be the difference in readout. But mostly they have the same fidelity, and that's because of the maximum native gate rank required.
So you've got some sort of fluctuations in there which correspond to the periodic boundary conditions on your rings, at least in the 1 qubit, so the non-lazy ones, because it's 4 and 8. But you don't really see that so much in the lazy 4-qubit ones. And what's
So say that again about the periodic.
yes, so you've got some sort of up and downs in the very top curve, which have period 4, which presumably correspond to going all the way around the ring. So your fidelity changes. This sort of comes through a periodic boundary condition. You see the same in the 8 one. There's a sort of
I don't think it's the periodic boundary conditions of the graph. I think it's that pattern that I showed you in the effective matrices, where if you have 2 1s, that means that you've had to go twice up to the Rydberg level. I think it's that as opposed to
okay, right, yeah.
So
But you still would need 8. Okay. Because that pattern is not in the 2-cube coin as such. Yeah.
I'll have to think about that. But yeah, I'm pretty sure it's from the effective matrices, because when I did simulations with basically smoothed out effective matrices, you didn't get any of those fluctuations.
This is not exactly relevant. Do you know why the IBM results look so weird?
Why they go no, not really. Especially the fact that they go up.
Yes.
So part of it, so I can't really explain this, but part of it is that it dips below the 0.5, and below the 0.5 is nothing. It's noise, and so you would sort of expect. So anything below the 0.5 mark is basically random. So I'm not sure why it consistently goes up, and I don't know why in the 4 qubit it quite clearly goes down and then up. I also don't know why they only ran them for a few steps based on size.
Yeah.
But yeah, the state prep with IBM is really bad, so that'll be why it drops like this. That'll be from state prep.
Okay.
But why it drifts up, I assume that's just randomness. But it's strange that it's quite down up.
Would you be able to get error bars on those? Did they have like a variance estimation on their error method or something?
That would only be if IBM gives us error bars. I don't think we'd be able to calculate error bars ourselves. And since they weren't in the paper, I assume IBM didn't give error bars. Yes. So we can conclude from this that we can sort of be doing 4-node and standard quantum walk on 8-node quantum walks, and we're sort of getting a quantum walk out of it. But anything bigger than that, and after 21 steps, you're not doing a quantum walk anymore. You could also, because the scaling is quite good at low steps, you could just do a couple of steps as, again, purely for benchmarking, not for any actual application, and you would be actually getting a quantum walk. And it might be interesting to compare different hardware at these very small steps. Would actually be interesting at the high steps as well, but you can't really say that you're doing a quantum walk. Yeah. And then the next thing that I did is I introduced the 4 qubit gate to our native gate set. So the lines in the lower opacity are just our results from the previous slide, with only maximum gate rank 3. Obviously, there's no standard quantum walk on a 4-node ring because you don't need 4 qubit gates for that. You only need 3 qubit gates because you have 2 position qubits and 1 coin qubit. And the fidelity increases are quite significant, especially at the 21 step mark. Yes, you get a lot more of these dips, these fluctuations, which are again from the way the affected matrices look. I assume this is also something that can be smoothed out with things like higher laser power. Again, we see that the ones with the same maximum effective gate rank have very similar fidelity curves. Yes. Okay, the next thing that I looked at is what if we don't have our native 4 qubit gate? What if we just improve our 2 qubit and 3 qubit gates? And then how much would we have to improve the fidelities of those 2 qubit and 3 qubit gates to replicate the fidelity results of the quantum walk with the native 4 qubit gate? So the ones in circles, that's with the native 4 qubit gate. The one in blue, that's the maximum native 3 qubit gate with the realistic error modeling. The other ones cannot be called realistic error modeling because they don't have those nicely physical error effective matrices. I've constructed the effective matrices by trying to keep the amplitudes and phases proportional to each other in the same way as the physical effective matrices, but I've largely made them up in order to manufacture these fidelities. What we find is that the curve that's most similar to the results with native 4 qubit gates have these fidelities. So 99.99 for the 2-qubit gates and 99.79 for the 3-qubit gates. These to me do not seem super likely, certainly in the near term. Seems much easier to just do this comparatively much lower fidelity 4-qubit gate. The other thing that I looked at is because these results say, yes, we would like a native 4-qubit gate. The worry is that because we only went to 16-node graphs with a 2-qubit coin, that's a 6-qubit quantum walk, and we want at least native 4-qubit gates on for a 6-qubit quantum walk. Do we want to be increasing our native gate set forever? That would be bad. So what I looked at, and again, these are not physical. These are not using those really nice physical effective matrices that Jared derived. These are just composite fidelities. So this is just the number of effective gates of each rank that each quantum walk of these sizes requires, and then we times all of those fidelities together to get our composite fidelity. So this is very sketchy, but it can give us a bit of an idea. So what we have here is that we have going from max gate rank of 3 to 4. So basically 4-qubit native 4-qubit gates, native 3-qubit gates up to native 4-qubit gates, and so on. And then we have our average increase in composite fidelity. And then in the inset, we have our just average composite fidelity. These, we already know that these aren't physical because they don't match with the results of the model. So we already know that these aren't physical. But again, it can give us a sort of idea of the pattern of changing your maximum native gate rank. And what we find is that you get a huge benefit from going up to 4 qubits, native 4-qubit gates, but not such a huge or greater ranks. So this is really good news. It means hopefully that for at least sizes like this, at least sort of hesitate to call these near term, but semi-near to further term sizes, we only really need native 4-qubit gates. So, in conclusion, for a 2-qubit coin on a 4-node ring, with these physical near-term gate fidelities, we find that our circuit fidelity is greater than 0.99 for 2 time steps and greater than 0.9 for 14 time steps. This can be increased to 5 time steps and 20 time steps if either we increase our 2-qubit and 3-qubit fidelities to these fidelities which seem out of reach in the near term, or simply introduce this native 4-qubit gate with this fidelity. Therefore, the native 4-qubit gate is highly beneficial for the implementation of quantum walks, especially in the near term. Native 5-qubit gates and higher ranks probably not so important, and so native 4-qubit gates seems from this to be our sweet spot. And then very quickly, also my conclusions for near-term algorithms. Certain algorithms are suited to certain hardwares. Please be hardware aware instead of doing hardware agnostic algorithms. Have hardware at least in mind, if not chosen as early as possible in your algorithms. Research estimations and complexity scaling require end-to-end analysis, which include things like state prep, encoding, decoding, readout. Gate fidelity is more important in the near term than number of qubits. Especially in industry, they love to talk about the number of qubits, and I do think number of qubits will be important for error correction. You'll notice that none of my talk includes error correction, and that's because we're specifically looking at near term. But beyond the next couple of years, I think we're going to see some really exciting developments in error correction, and I think that's going to be a game changer for quantum computation. And then number of qubits will become more more interesting, but for the moment in the near term, gate fidelity is way more important than the number of qubits, and error correction will be required to compete with classical. Lastly, I'm plugging this review here. Really beautiful review done by Rhonda and Viv in my group, as well as Bruno and Oma. It's a very, I would say, level-headed review of quantum computation, quantum algorithms for scientific computing. It talks a lot about what I talked about today, and it goes further on to go beyond near-term stuff, to think more about further term, to think about fault-tolerant computation. And yeah, I would highly recommend. Thank you for listening.
Number of steps, 1 and 2 and 21. Like for application in, for instance, physical, like motivated application, do you have an idea of like what number of steps could be interesting for quantum algorithm?
I'm not sure exactly, but much higher than I've been looking at, so at least in the hundreds, if not thousands. It's hard to know exactly how time step. So for different applications, time step will be matched to different real time. So yeah, it kind of depends on the specific application, but I would say hundreds, if not thousands.
Going back a bit, with the, you were saying the finite blockade radius.
Yeah.
Could you go over why that happened? I kind of didn't understand.
So it's basically there's a decay of the there's a decay of the strength of the blockade radius the further you get. So if you're in this representation here, your qubits are right in, they're not really the corners, but right at the edge. And that's not a good place for them to be. Ideally, you want them to be much more central in the blockade radius. So you have to think about exactly your separations in your array. They need to be close enough to each other that they're not going to, that you can address them individually, but not too far away. That's the blockade radius won't properly work. So there's sort of a give and take there. I'm not super up on the specifics of how they choose that give and take.
But if I understand correctly, the blockade is a feature of the neutral atom.
Yeah.
How you can perform some control operation.
Yeah, it's a physical thing to do with the Rydberg state.
But it's not a problem, right? It's
no. It's yeah. It's just it's just when you think about the architecture of your array, you've got to get it just right.
Yeah.
But it would also, I'm guessing, affect compilation, right? Because it means you can only accept one atom in the neighboring. So you kind of have to take that into account.
Do you mean the rank of the native gates? So for example, with this architecture, you can only ever have 3 native 3-qubit gates. And then that's why I said this should say triangular or rectangular, because if you want to do native 4-qubit gates, then you need a rectangular array. Or ideally, which we don't have yet, a 3D array with a pyramid structure. That would be even better than a rectangular array. But to my knowledge, nobody's done that yet. Yeah.
Thinking about algorithm customization for hardware. So the quantum walk algorithm, you've got your representation doesn't really care about the phase of things because everything's just 1 or 0. And so does the phase variance that comes out of your hardware mean that that's a good, it doesn't matter so much because Yeah, I was just trying to think, because
So that's interesting.
Yeah. you're only really needing to represent, is it there or is it somewhere else, rather than some, the particular relative phases of things.
I would need to go and look at it specifically, but it sounds like that would be true.
But you also need interference, right?
So that's what I was thinking, like because of the destructive I'm not sure, especially because my again with my sort of made up effective matrices, I didn't play about too much with them because I wanted them to match the physical effective matrices. It would be very interesting to use exactly that model and see what happens if the phases are super bad, but the amplitudes are okay.
Yeah.
That's a really good idea.
There's a slightly speculative question. So in this one, you've got these circuits which have these like lots of multi-control NOT gates. My understanding is what you've done here is found hardware efficient ways to implement them. But what you're ultimately trying to do is implement like an increment gate. And I'm aware that there are kind of slightly more efficient ways to like transpile them. So like at least in the computational Steve gate set. So I guess my question is there a comparison against that kind of method?
Not yet, but that's definitely something that I want to look into because so the thing that's sort of cheeky about this is that instead of coming from the quantum warp side and then identifying that Rydberg atoms would be good for it, we instead came from the Rydberg side and then looked for an algorithm that would be good for Rydberg atoms. So it is a cheeky way around of doing it and not one that I would recommend. So yes, I definitely want to look into that because there are different ways of both encoding and also your gate circuit.
If you want algorithms with lots and lots of topology, and then topology is a big one.
Yeah. So the way that I came into Rydberg atoms is because I was looking at concentrational entanglement, which requires controlled swap gates, which have toffolies in them. So again, that's why we looked at neutral atoms for that specific application, and that's a more because we're only using toffolies and not these huge control gates, control gates. It's way more near term. But yeah, I definitely want to look into different ways of doing things.
So I'm curious about something. So could you go to the slide where you have the different noise models for the C batch and the C that?
So this one.
Some more please. I think this one of the slides more. No, this one. So yeah, this one.
This one.
Exactly. Yeah, so I was curious about the slight dip at step 1 and
That's one,
step
yeah.
15. So is this like a feature of the quantum walk simulation?
I don't think so. Again, I think this is a feature of how the effective matrices look. If you have smoother effective matrices, then you don't get this dip.
Okay.
If you have, by smoother effective matrices, I mean where all the amplitudes are the same, instead of having a function in terms of how many excitations you have. It is interesting that it's in the same place
Yes.
for both the maximum gate rank 3 and 4.
That happens to a small extent for the 20 case for the red one. Yeah, so I don't know what's.
But yeah, basically what I'm going off is I did some super symmetric effective matrices and it was super smooth fidelity lines.
I think something nice. No, it's that one last organised.
It is.
Thank you very much. We don't have things yet, but we do have things.